Okay, let's have a look at this concept of the common ion effect and how it affects solubility. So if we draw a plot of a graph of solubility of an ionic compound such as lead chromate or any other ionic compound, and we plot that against an increase in concentration of another compound that has a common ion in it, what we find is that the solubility of our first compound decreases with this increase in concentration. But why does this occur? Well, if we take our compound down here, we split it into its component ions. So we have potassium and our chromate. We notice that we have a common ion of chromate with our lead chromate, which is what we're looking at. And now if we go back to our original substance and we write our equilibrium reaction, so we've got lead chromate dissociating into lead ions and chromate ions, this part here being in common with this part, we find that there's an effect on the system if we increase this concentration. If we have a look, because we've got this one in common, we're effectively increasing the concentration of chromate ions in solution. And as we know from Le Chatelier's principle, if we do that to one of our products, we shift, or the reaction will shift to the left to compensate for this increase in concentration. So our potassium chromate, because of this shift to the left, becomes less soluble. In other words, the solubility decreases with an increase in concentration. And this is known as the common ion effect. So as the concentration of common ion increases, the solubility of our given compound decreases. Let's have a look at this in action. Let's say we're asked to calculate the maximum barium concentration in a 0.01 molar aqueous solution of sodium sulfate. Now we're not told that it's barium sulfate, but in the next part of the question we've been given a KSP for barium sulfate as 1 by 10 to the minus 11. Now we're going to do this problem in two parts. First of all, I'm going to show when there's no common ion, and we're going to calculate the concentration of our barium, and then we're going to show it when we have the common ion present. So first of all, let's look at it when there is no common ion present. First step in solving this type of problem is to set up our equilibrium reaction. So our barium, or our barium sulfate, is the compound in question. So we set that up in equilibrium with its ions. So it dissociates the barium ions and sulfate ions. Now, we'd normally go through the initial concentration, a change, and then our equilibrium concentrations, but for this part we don't need to do it. Instead, we need to use our KSP to calculate the final concentration at equilibrium. So our KSP expression will be the concentration of barium ions times the concentration of sulfate ions, and that will be equal to our KSP value of 1 by 10 to the minus 11. And this is a 1-to-1 ratio, so x squared will equal this, therefore x will equal 3.16 by 10 to the minus 6 molar. And this will actually be our concentration of our barium ions and our sulfate ions. Remember, this is where we don't have any common ion. So let's look at it now where we do have a common ion. So once again, we follow the same step. First step is to set up our equilibrium reaction, as we've done. This time, because we've got a common ion, we need to set up an initial set of conditions, a change, and an equilibrium. So initially, we don't have any barium ions in solution in our sodium sulfate. However, we do have sulfate ions present, and we've been told it's a 0.01 molar solution. Therefore, our sulfate ion concentration will also be 0.01 molar as well. Now, as this shifts to a new equilibrium, we get a change. So our barium sulfate from our original part of the question is put into solution. Some of it will dissociate, we're just not sure how much. So we get X, and we also get a 1-to-1 ratio, so we also get X sulfate ions in solution as well. And at equilibrium, we've gone from 0 to X, so we've now got X moles per litre, or X molar at equilibrium, and our sulfate ions, we started with 0.01 molar, plus our change of X, so we get 0.01 plus X. We then follow the same step as we did over here to set up our equilibrium expression, and we substitute our KSP value in, and we find that we get X times 0.01 plus X. Now you'll notice I've crossed out the second X. We could go through the quadratic formula to solve this equation. However, there's another simpler way to do it when you get really small values for KEQ or KSP. And what we're saying here is with a small value, not very much will go from the left to the right-hand side. So effectively, this x will be much, much smaller than our original concentration. Effectively, it's 0. So instead of being 0.01 plus x, we can effectively say it's 0.01. So we can now solve for our x, and we find that x is equal to 1 by 10 to the minus 9 molar. In other words, our sulfate ion concentration and our barium ion concentration in this new system will be 1 by 10 to the minus 9 molar. Compare these two values and we see that we've had a significant reduction in the concentration of our barium ion from solution that's in pure water to solution that contains a common ion.